Greetings and salutations. Today, this presentation will be covering the material selection behind tennis racket frames and why the choice of materials directly shapes the racket's performance. Historically, racket frames evolved from wood to metal and eventually to carbon fiber reinforced composites, CFRP. As shown in the slide, wood was heavy and flexible. Metal improved stiffness but added vibration, and modern composites finally achieved the stiffness to weight ratio that players actually wanted. This evolution wasn't about fashion. It happened because, engineerically, players started hitting harder and the old materials couldn't return energy efficiently or survive repeated impacts anymore. During a ball strike, the ball compresses, the string deforms, and the frame bends. Depending on the material, that energy is returned to the ball or wasted as vibration. Power comes from the efficient energy return. Control comes from frame stability, fine and minimal unwanted deformation. And then comfort depends on how much vibration the frame can dampen. Because of that, racket performance is governed heavily by the material's mechanical and physical properties as well as the geometry of the frame itself. Everything a player feels, the power, the comfort, and the control, ultimately comes down to density, stiffness, strength, structural design, and cost. Starting with density, density controls the racket's mass, swing speed, and the handling as well. A lighter frame swings faster but may lose stability, while a heavier frame feels solid but becomes slow. Low density materials like carbon fiber composites lets engineers keep the racket balanced without making it feeling sluggish. Density is basically the foundation that every other design choice depends on. Next is stiffness, or the elastic modulus, which determines how much the frame bends during the impact. Higher stiffness means less bending and more energy returned to the ball, so you get more power. But the stiffness isn't but a lot of stiffness isn't automatically good. If it's too high, the frame becomes harsh and sends more vibrations to the player's hand. Moving on to the strength. The material needs high yield and tensile strength so that it doesn't deform or crack under repeated impacts. Every ball strike puts the frame through tension, compression, and bending. If the strength is too low, the frame slowly warps or fails, which obviously ruins performance. Structural design also plays a huge role. Beam thickness and the geometry of the frame directly influences stiffness, the optimal hitting spot, sizes, and the overall stability of the frame and the racket. Wider beams of the throat increases stiffness and therefore power, while thinner beams will improve the feel but also reduce the stability of the racket itself. Mass distribution also shapes the racket's swing weight. A heavy head would rack a heavy racket would give more power and plowing power through the ball, while a headlight racket offers better maneuverability and control. This mix where composites make it easy to fine-tune this mass placement, for example. Finally, cost. Material cost needs to balance stiffness, strength, weight, and manufacturability. It's a multi-criteria engineering decision and not just a price tag. High modulus carbon fiber, for example, gives a good performance, but is extremely expensive because of labor-intensive layups and precision curling cycles. But cheaper materials like aluminium and relative or low-grade graphite reduces costs, but they're heavier and have worse vibration dampening. They're fine for beginners, but the trade-off is that it's not ideal for larger competitive play. And those are the key material factors that determine how a tennis racket frame performs. Moving on to you, Anson.
Thank you, Xavier. Now I will continue with the material explanation and justification. Three materials are selected and compared, which are Ti6Al4B titanium alloy, T300 carbon fiber exposing composite, and exposing as glass fiber. Ti6Al4B titanium alloy, also known as graphite titanium, derived its name from the proportional composition of its constituent metal with approximately 90% titanium, 6% aluminum, and 4% vanadium. The alloy offers a density of 4.43 gram per cm cubic, a tensile strength of 1,170 megapascal, a yield strength of 1,100 megapascal, and a stiffness of 140 gigapascal. As player, we are more focused on the yield strength as we don't want the frame to undergo permanent distortion or bending. The alloy is more suitable for a diamond-shaped racket, which prioritizes power over control by concentrating its weight in the upper parts. The average cost of the alloy is around $70 per kg. It's because the complex extraction process of titanium O-ring, which require high energy consumption. Besides, the high hardness and tensile strength made the CNC process difficult as the cutting tool will wear faster and require frequent replacement, which is costly. T300 carbon fiber explosive composite is classified under carbon fiber reinforced plastic category. A composite consists of two phases, which are metric phase and dispersive phase. The metric phase protects the underlying brittle carbon fiber, while the dispersive phase enhances metric properties, resulting in a composite that combines the strength of both the material and inhibit their average mechanical properties. The composite offers a density of 1.55 grams per cm cubic, an ultimate tensile strength of 1,800 megapascal, a stiffness of 150 gigapascal. Ultimate tensile strength is typically used for composite because the failure begins when the fracture starts. The composite is more suitable for a round-shaped racket, which prioritizes control over power by distributing its weight in all parts. The average cost of the composite is approximately $35 per kg. It is because its huge market potential attracts worldwide investment to develop many advanced technology to help reduce costs substantially. Next, exposing S-glass fiber is also a composite and is generally composed of exposing resin as metric phase and S-glass fiber as dispersive phase. The S represents the high silica content. The composite offers a density of 2 grams per cm cubic, an ultimate tensile strength of 1,700 megapascal, and a stiffness of 50 gigapascal. Due to its medium weight, the composite is preferable to be formed into a teardrop shape, which gives balance between control and power. Its average cost is approximately $25.3 per kg. On the chart, it can be observed that the T300 carbon fiber exposing composite has the lowest density while inhibiting the highest tensile strength and highest stiffness among all the materials. Only its average cost is slightly higher than the exposing S-glass fiber and is given 2 points only. For the frame geometry, each material is assigned the most suitable shape to maximize its performance, and therefore all are given 3 marks. After calculating the total mass, T300 carbon fiber exposing ranks first and is the most suitable material for a tennis frame. Now I'll pass time to Edmund.
Thank you, Anson. Now, although the T300 carbon fiber epoxy composite is the optimal choice for tennis racket frames based on its key properties, it is important to view how sustainable it is. Therefore, let's explore the sustainability of CFRPs, which are carbon fiber reinforced plastics. The first sustainability benefit is that CFRP has a trade-off between its upfront emissions and potential use phase savings. Based on the two diagrams, it shows that the virgin carbon fiber production requires a high energy intensity of 262.3 to 464.2 megajoules per kg. The high energy consumption would play a major role in environmental impact, as some of the raw materials needed to produce that energy may emit greenhouse gases. This includes the burning of fossil fuels that produce carbon dioxide. However, remember how CFRPs are low in density? What that means is that it is a lightweight material. This causes the fuel consumption of vehicles such as cars and planes with parts made from CFRPs to be much lower. Therefore, it compensates for the environmental burden caused by its energy consumption by reducing the fuel consumption of vehicles to be more environmentally favorable. The next sustainability benefit is that CFRP waste can be recycled or repurposed. For example, CFRP scraps can be used in cement matrix composites such as concrete. This will naturally improve the mechanical properties of cement mortar, which includes the flexural strength and ductility. This helps reduce the use of virgin materials such as sand and cement in the concrete mix. Additionally, it also reduces landfill disposal and decreases the need for producing carbon fiber, which requires a lot of energy as mentioned in the first sustainability benefit. Here is the example process of how CFRP waste can be repurposed. Carbon waste are collected and heated at high temperatures. Subsequently,
The carbon waste is grinded and undergoes sieving to separate unwanted particles. Finally, the carbon fibers become small and are ready to use to act as the fiber phase for cement mortars. The final sustainability benefit is that CFRPs can be repaired, bringing economic and environmental benefits. According to a life cycle costing test report, CFRP is economically sustainable for manufacturers. The diagrams with S1, S2, and S3 refer to the three different costs of producing a CFRP material. The two tables include the cost for both of CFRP materials, whether the matrix phase is made from fossil fuels or bio-based chemicals. You can see that the NPV, which stands for net present value, of all scenarios for both tables is positive. This would mean that repairing CFRPs is economically beneficial. As for the perspective of environmental benefits, it is shown in this graph. Dark blue and gray bars represent substituting the CFRP materials entirely, whereas the dark pink and light pink bars represent repairing the CFRP materials. The percentage shows that the level of impact of these methods of obtaining CFRP materials on the environment, such as climate change and human toxicity. It is noticeable that the dark pink and light pink bars are shorter than the dark blue and gray bars for most areas of impact, indicating CFRP materials to impose less environmental impact than substituting. The environmental impact is reduced up to 50% when repairing CFRP parts rather than producing new ones. To sum up our findings, the T300 carbon fiber epoxy composite is the best material for tennis racket players based on its properties of having high stiffness and tensile strength, round shape for control, low density for lightness, and relatively low cost. It also shows strong sustainability benefits, such as low fuel consumption, can be recycled, and has repair benefits. This is our list of references. Thank you for listening to our presentation.